You have a challenge. People are hungry. Keep them with us.
Okay, I'm hungry too. Let's see. Set a timer for 20 minutes. Okay, good. So what I've just done there is actually run some machine learning actually on my watch to understand that sentence and set a timer. And that's really what this talk is all about. So what I'm going to talk to you today about is what you can do in terms of running machine learning on Cortex-M microcontrollers. So first off, let's kind of go through a little bit of the terminology that I'm going to use, so as we've got some common ground. So, so what I'm really going to be looking at is machine learning, the third row of this, or third ring of this onion here. And what we're really talking about when we talk about machine learning is the construction of a mathematical model that you can train with a set of input data, and you construct this model, generally training it in the cloud rather than at the edge. But once you've got this model trained with a data set, then you can run this model against a set of data. And once you've run that model against a set of data, you can then infer whether or not something is true or false within a specific percentage of probability. So, for example, you might take a data set that's a series of photographs of animals, and you might build a model that basically says whether they're a cat or a dog or a giraffe. And then when you show a photograph to this model that you've trained up in this way, it will actually give you a percentage probability of whether it's a cat or a dog or a giraffe or something it doesn't basically know. So that's kind of what actually happens today. But generally, these models have been run up in the cloud. They're trained in the cloud and they've run in the cloud. But what we're going to look at is how we can actually make these models run on a wee tiny small Cortex-M microcontroller. So why do we want to run machine learning at the edge? And I think this comes back to the slides and presentation that Mark Hamilton did yesterday in the keynote. If you're uploading a lot of data into the cloud to do your inference, you're going to use a lot of bandwidth, and that's time consuming and it's also cost consuming as well. Running stuff in the cloud is great, but it does tend to be rather power hungry. It would be great if we could run at the edge and we could maybe run these inference engines on batteries, for example. That would be great. And latency is another issue. If I say a sentence to my assistant and I have to wait several seconds before it actually comes back with an answer, that's also undesirable. And then reliability is another issue. It's very much dependent on your connection into the cloud. So if you're driving along in the desert and you suddenly lose connection with your cloud, you'd be rather unhappy if your self-driving car just stops because it doesn't know where it's going. And then lastly, another reason for running all of this stuff at the edge is security. You want the data that you're using to feed your inference engine preferably to actually reside on the device that you're running it on, not go off into the cloud, and who knows where that data might go, as we're seeing in the news today. So what am I talking about in terms of running on Cortex-M? So, you know, at the high end of running at the edge, you would have autonomous vehicles, you know, with fairly large processors actually running in the car. You know, it's like a mini data center running in the boot of your car. But what I'm really looking at is what I can do with a Cortex-M processor down at the tens of milliwatts, way down there. So in this domain, I can do things like rudimentary image detection, pattern training for sensors, so maybe sensors all fused into an inference engine for looking at anomalies in industrial processes, looking at movements around smart buildings, things like that. And then way down to the basic keyword detection, where you actually want to be able to talk to things. So today, if you buy an Alexa device or something like that, you're actually looking at a fairly heavyweight processor. Or if you buy, say, a Google Home, you're looking at a fairly heavyweight processor. But what's really desirable is to be able to reduce the cost of these processors, get it down to something a lot smaller and a lot cheaper. And then you can actually start talking to things like your light bulb or your light switch to turn things on and off. And I think there's going to be a growth of these kind of platforms over the next couple of years. It could be quite an explosive growth because we've all seen the advent of wearables like this, devices that go into your shoes, all of that, health tracking, that kind of stuff. So deploying machine learning into these kind of devices is going to be really, really big, I think. So there's an explosive growth for machine learning, I think, on small microcontrollers. So for the rest of this presentation, what I'm going to do is walk you through the process of deploying a neural net model on a Cortex-M device. So what we're going to look at is speech recognition, so recognition of a small vocabulary, that kind of thing. We're going to develop a trained neural net model, and we'll then deploy that neural net model onto a Cortex-M, and we'll optimize it so as it runs really, really efficiently. So the steps for doing this involve deciding what kind of neural net model you're going to use for your application domain, translating that model, once you've got it, into something that can be deployed onto the microcontroller, because large-scale neural net frameworks simply won't fit, and then using a set of optimized functions to allow you to run the model fast, run the model small, and run the model energy efficiently. So let's have a look at the choice, how we go about choosing a neural net model. So for something like a vocabulary recognition, keyword searching, that kind of thing, there are a number of neural nets that are neural net models that are actually applicable. And when we look at the Cortex family of processors, we can basically classify them into small, medium, and large. And the small-scale ones are actually quite interesting. There's quite a lot of these out there. So doing something on a reasonably low-cost device, which has got a small memory footprint and a reasonably constrained performance envelope, is really the area that we want to look at. So up until recently, we saw that there were a range of different neural network models that were applicable in different scales of operation versus memory. So down at we've got large, medium, and small here, and down at the small scale, up until recently, the long short-term memory model neural net seemed to be the most applicable and give you the best accuracy for memory size versus operations. But we did our own research into this, and we looked at a series of these different neural net models. And what this basically shows is a three-dimensional map of the different models, where we have accuracy on the y-axis, and we have the number of operations it takes to get to an inference in the x-axis. But the size of the bubble or the size of the blob represents the number of parameters in the model, or effectively the number of weights in the model. And if you have a very large number of weights, then of course your memory footprint goes up considerably. So really we're looking at accuracy versus number of operations versus memory footprint. And from this research, we actually found that a convolutional, or a CRNN, a convolutional, got to look at my notes, I think it's convolutional regressive neural net is actually the best fit for this, because it actually has a really small number of operations relative to any of the other networks, but still gives you a low number of parameters and a high level of accuracy. So if we tabularize this, what we find is the bottom two lines here of this table show that between a depth-wise separable CNN and a CRNN, we actually have a trade-off. And that trade-off is the number of operations to get to an inference versus the amount of memory. So if you have a CRNN, you're at about 80K bytes, but you're only using 3 million operations to get to your inference. Whereas a DSCNN, you're actually got half the memory footprint, but you've nearly doubled the number of operations you want to do. So it's kind of as we would say horses for courses. You need to choose whether you want a lower memory footprint and a higher energy envelope, or a larger memory footprint and a smaller energy envelope. So it's all about energy versus cost, really. So we've talked about choice of models. What I think we should do now is talk about how that model gets compressed down to an executable program that can run on a Cortex processor. So to do that, Arm has put together a series of tools to help you do this. So one of the most important things to do when you want to deploy your model is to reduce the accuracy of the weights. One of the interesting features of machine learning is that once you've got a trained model and you've got it working and you've got the accuracy that you require, you can actually reduce the floating point accuracy of the weights that you use considerably. And you can go from 32-bit floating point right down to 16-bit or even 8-bit fixed point for your weights. And as this table shows, as you go to an 8-bit quantized model, in fact, in the case of CRNN, you get just slightly, although it's in the noise, slightly more accuracy than you had with the 32-bit floating point. So quantizing things down can actually greatly reduce your memory footprint, but still allows you to have the same level of accuracy. So Arm has put together a series of libraries and tools, part of its Project Trillium endeavor, which was announced a few weeks ago. And as part of that, there is an SDK called the ARM-NN SDK. And part of that will actually have the tools that you need to compress down the network into something that's executable. So once you've got your executable program, you also want to be able to hopefully run it efficiently on the Cortex-M. And so for that, we actually introduced at the beginning of this year Cmsis-Nn. So Cmsis is an industrial standard that Arm brought out a few years ago that enables, if you write to the Cmsis APIs, it actually enables you to interplay and exchange different ARM-based microcontrollers, because you just write to the Cmsis standard, and if the Cmsis standard is supported by the microcontroller, then it will run, the code will just run on any of those microcontrollers. So as well as Cmsis core, depending what you want to do, there are packs, Cmsis packs as they're called, for real-time operations, like there's an RTOS there. If you want to do DSP operations, there's a Cmsis pack for that. And there's now a series of optimized operators for neural nets called Cmsis-Nn. And that's available free on the Arm GitHub today. One of the other things that we have is also the ability to measure energy consumption on the microcontroller. So you can actually do some of the trade-offs I described earlier around memory footprint versus number of operations. So Cmsis-Nn provides you with a set of optimized routines for some of the common operations that are done by inference engines. That includes SIMD operations. It provides tools for minimizing the memory footprint. It also provides a series of data formats that you can basically relay out your network in a data layout that makes it much easier for the microcontroller to actually execute on. So here's a little look at the kind of performance you can get, performance improvement you can get if you use Cmsis-Nn. So you can get roughly, using these operations that are part of Cmsis-Nn, you can actually improve the performance by nearly 5%, but also, by 5 times, sorry, not 5%, 5 times, but you can also improve the energy efficiency by nearly 5 times as well. And so that in an MCU space is really very interesting. Okay, so lastly, I wanted to talk a little bit